Started. We just have one more chapter left to cover, and this chapter is going to just be a survey of nuclear chem. I know there's not that much time, so you actually don't have to read this chapter. I'm just going to test you on the stuff that we talk about in class.
I was wondering if you could generally discuss or suggest what topics we should focus on for the final.
The final is actually, every topic is going to be on the final.
Is that 25?
No, 25 is going to be on the final.
Will this be emphasized more?
No, I mean, there'll be some questions from 25, but it's not going to be like one half the test is going to be on 25 and 24, and the other half on the other material. It's just like if you take all the chapters and kind of distribute them evenly. In the past, I've said there would be a few more questions from this, but not really.
And for 24, are we expected to know how the reactions proceed? Because like when some things like react, they come up with like weird products for chapter 24.
Are you talking about the synthesis? I mean the
formation.
Geometric isomers.
So it's kind of like weird to like predict what's gonna come out. Or
Can you give me an example of a problem?
More about 24. I don't have to listen, but
Okay.
it's some of the.
Let's see if I can, let me go to the e-text here. We could take a look at the homework really quick and then see. No, I mean some of the. Do you guys remember the reason behind skeleton redox? The reason behind skeleton redox is because there's so many variables you can change: temperature, pressures, concentrations, et cetera, all these things can impact the products that you form. And so the whole idea behind skeleton redox is just to try it and see what happens, and then just determine what the major products are. So you don't really predict anything there. And for example, if I told you to give me the exact conditions where burning methane is going to produce 80% carbon monoxide, 20% carbon dioxide, are you going to be able to tell me the exact conditions under which this combustion of methane produces that much carbon monoxide? Probably not easily, right? I mean, you could try doing some calculations of Spartan and other things, but in the end, you just have to try a whole bunch of things and then see what happens. And so chemistry is this two-pronged thing. The chemists always approach things, they want to use as much theoretical knowledge as possible, because the more theoretical knowledge you use, the less you have to do as far as work goes in the lab. But it's too hard to predict sometimes, theoretically what exactly is going to happen. And so this is why the other side of the coin is to just try it and see. And when you try it and see, I think in Chem 1A I talked about mini reactors. Mini reactors, like your spot plate. Your spot plate in the drawer, and I don't think you guys used it except maybe for the Le Chateliers, but in the spot plate in your drawer, you can run like 8 reactions at one time, right, or something like that. But these mini reactors that they have that are just tiny, you could run 1,000 or 2,000 reactions simultaneously. And what they do is they just change certain parameters slightly to see what impact that makes on it. And so some of these, well, let's see, did they ask you to predict? If they asked you to predict the products,
I guess I'm just kind of asking, like, what are you going to be expecting out of this chapter?
All right, which problem was that, if you can recognize? Was that an advanced problem? No?
Yeah.
22? 36? 36?
Yeah.
All right.
Sorry.
26?
We'll get there.
I can't scroll right. what's wrong with this? I still haven't figured out what's wrong with this scroll. What's on this?
I think you might have to close that bottom window and then maybe try it. It might work. Sometimes it's the top window.
All right. All right. Hopefully it can scroll.
That's all of it.
All right, write equations to represent the following observations. You see, they aren't even, this is not predicting reactions. This is going back in the book and looking what copper solution is yellow. And so you flip back in the book and you look, because they're telling you the major product here. They're telling you the major product and they're only identifying by color. And so that's all you can do is to predict that. And so this one, you aren't actually predicting, you're just using these little clues and going back and looking at the colors that they give you here. And so if we look at what copper solution is yellow, then it's too slow. We go back in the chapter.
There's two, but there's one that's really yellow.
And then, what page are you on, John?
1096.
Okay, here I am, 1096.
That's what you're talking about.
Yeah, this is what I'm talking about here. And so we aren't really predicting anything. We're just trying to use physical clues, observations, and to figure out what the product must be. And so if we look over here, well, the product's either got to be due to tetrachlorocuprate 2 ion, okay, which is this. When a small amount of water is added to the mixture, we have yellow-green when we get a mix of the tetraaqua, copper 2, and the tetrachlorocuprate 2, yellow-green. When then we get the blue of the tetraaqua. And so it's just, we have yellow and blue make green, that kind of thing. And so yellow is this. And so it's not really, and anyway, that particular problem relies on having open book, right? Having access to other information. But it's not predicting from the rule, I mean, you can take some guesses, but they're telling you what the product is. Okay? And so, unless I told you, I wouldn't expect you to predict. Yeah, I mean, I would expect you to be able to guess some potential products, But we haven't really talked about much of the, for these Lewis acid base, remember what I said about predicting Lewis acid base reactions? Anybody want to remind me? What did I say about predicting? Yes, Kelly?
You gotta use LCAO, molecular orbital, valence bond is hard.
You don't use valence bond. We don't use valence bond. We just use
LCAO.
LCA. Well, LCAO is molecular orbital theory. We use molecular orbital theory. Now, how much of molecular orbital theory do you know? And I just said it in passing. Somebody tried to come up with some simple rules for predicting. And those simple rules for predicting are called another acronym, 4-letter acronym. What was it? Hard, soft, HSAB, hard, soft, acid, base. This guy, actually he was at UCSB for a while, but he was a pioneer in HSAB to make it easier to predict these things. Otherwise, it's pretty hard to predict. And so with HSAB, you can make much more accurate predictions, just without doing any calculations. Otherwise, you would do calculations in C, like you do Spartan type scenarios. You could do reactions in Spartan as well. But Spartan's going to tell you the thermodynamics. It can also tell you the kinetics if you do transition states, but you have to guess some transition states as well. The thermodynamics is just the overall driving force. It's not going to tell you how fast it's going to go. Although we can infer some stuff about the kinetics, usually things that have a very high driving force are going to happen fast, like explosively, usually. But, you know, this combustion of methane has a high driving force, but does it happen fast?
No.
It happens very slow at room temperature.
Wait, so then, why does not methane have the rate law of CH4 times O2 squared? Why is that false?
Because, why is, well, that's a good question. Why is it false? Because it's, I just said it's a fast reaction. Term molecular collisions are slow, right? Slow reactions, you'd expect it to be. In general, term molecular collisions are kind of rare. This reaction speeds up quite rapidly, you know, at elevated temperature. And so when you look at how fast this reaction actually occurs, you know, well, you know, burning flame occurs very fast. Then term molecular is likely not it. You know, just one step. But anyway, that was not, you know, that particular one was not having to know the mechanism. That particular one was, you know, give the best answer. Giving the best answer, you know, I mentioned that the combustion of methane occurs in how many steps?
100, 1,000.
Yeah, you know, it wasn't until recently, you know, but there are hundreds upon hundreds of potential collisions that can occur in the flame.
Wow, baloney?
What's that?
No.
Okay. All right, is that it for the questions from chapter 24? Okay, nuclear chem follows a different set of rules. You know, what's the most important thing in you know, quantum, what does quantum do? Quantum looks at, you know, how the electron cloud is distributed, right? And electron clouds can tell us about positive and negative regions, you know, red and blue regions, or blue and red regions. Positive is blue, red is negative. And so charge, electrical charge is very important in chemistry. And electrical forces dictate all of chemistry, basically. All of chemistry depends on electric forces. Nuclear chemists, they don't care about the charge. For those of you who hate writing charges and net ionic equations, you know, I don't, there's like maybe about a few % of people who never write the charge in net ionic equations. You know, just write NO3 without the negative charge. You would be okay in nuclear chemistry. So you might think about nuclear chemistry because nuclear chemists don't care about the charge, you know, because charge is no big deal. Basically, electrical charges are minor in terms. And what nuclear chemists look at is a different force. What's a different force in nature? The electrical forces, gravitational forces, a different force. Nuclear forces, how about that? Nuclear forces are strong forces. Strong because they're very strong. I mean, they have to be very strong. If you're going to clump a bunch of protons, let's say you're going to cramp 92 protons in the nucleus, like in uranium, you know, what's holding all those 92 positive charges together? You know, it's got to be a strong force because the amount of repulsions, electrical repulsions, will be enormous, right? But, you know, there's a limit, too, because, you know, we know that when we get to something like 92, in fact, even before 92, you know, when we're getting to like 84, when you get up to like 84 protons, you know, that's pretty hard to keep together. Right? And so from element 84, do you see the molar mass isn't so well or accurately determined? You know, got these parentheses around there. That's because polonium is radioactive. Polonium, in fact, was used for the assassination of journalists.
Is that why lead is so toxic? Partly.
Well, lead is stable. The nucleus of lead is surprisingly stable. You know, it's 82. protons, but it's very stable. Lead is reactive because lead is a soft metal, and you have some soft like sulfur-containing proteins in your body, and sulfur loves lead, and lead can really disrupt your. It's a heavy metal. Heavy metals are soft metals, and they end up disrupting protein.
Lead poisoning.
Lead poisoning. But its nucleus is stable. And so, but here, once you get these like polonium, radon, etc., those become radioactive because the nucleus is unstable. Right? And so, this chapter, nuclear chem, we're looking at the nuclear forces, the strong forces. And they're going to be naturally occurring radioactive isotopes like radon. There's a lot of radon. In fact, around here, people who live with the granitic soils, they get a lot of natural radon, so they recommend good ventilation. We don't have that much around here, except on Palos Verdes, there's quite a bit of radon.
Radon pretty toxic.
Radon is very toxic, yeah. Radon is, nucleus is unstable. Right? The nucleus is unstable and it decays via alpha radiation. But the problem with radon is it's a gas. It's an inert gas. Chemically it's unreactive because it's like all the other inert gases, but unfortunately its nucleus is unstable. And so if you were to inhale radon, and it emits an alpha particle, that alpha particles are highly reactive because are alpha particles themselves radioactive? Are alpha particles themselves radioactive? Well, an alpha particle itself is not radioactive because an alpha particle itself is made up of helium, right? The helium nucleus is extremely stable. But the problem with an alpha particle is, it's a helium with a 2+ charge. And if you think about a helium with a 2+ charge, is that going to be a very happy species? No, it's going to be an extremely powerful oxidizer. And so it's, what would we say? It's oxidation potential? Or we say it's reduction potential? We'd say its reduction potential is extremely high. Would you say it's higher than the strongest on the chart, fluorine? Way stronger. An alpha particle is off the chart strong.
You got to drill the hole into the ceiling.
Right, yeah, you got it. You have to drill a hole into the ceiling, and then you can place alpha particles way up there. Because alpha particles are going to be way up there. And so this is what we call ionizing radiation, because what it's going to do is it's going to strip electrons off whatever it comes into contact with and ionize it. Right? And what it strips electrons off is your lung tissue, right? You inhale it, and then you do it again. But maybe, radon doesn't react with anything, so you exhale it. The person who got the polonium, though, they ingested the polonium. I think they tried chelation therapy, they tried a whole bunch of stuff to get rid of the polonium out of their heavy metal. But it wasn't enough. The person, what can you do if you have a bunch of polonium atoms in your body giving off alpha radiation? But the lucky thing about alpha radiation is it is such a powerful oxidizer. If it's such a powerful oxidizer, then a sheet of paper will shield yourself from alpha particles. Why? Because paper is electron rich, it's combustible. And so it's a good reducer, and then alpha particles, a strong oxidizer, you get a redox reaction, so you can shield yourself.
Particles go up to fairly large particles.
Mm-hmm. Alpha particles are extremely small. Rutherford used alpha particles to shoot, gold foil.
What comparison to gamma and beta? I thought they were
Oh yeah.
the biggest.
Well, gamma and beta are let's go with beta. Beta or electrons. essentially. And so how big are electrons?
Alpha particles to the gold foil. Some of them hit and some of them.
Well, okay, electron's mass is very small, but how big is an electron? How big is an electron physically? This is Chem 1A material. How big is an electron? We know the size of the nucleus. You know, it's like 10 to the minus 5 angstroms in diameter, right? An atom is typically like an angstrom or tens of angstroms in diameter. And so, know the size of the nucleus. Well, what is the size of an electron? Well, we know the mass of an electron, we know the charge of an electron, but how big is an electron? Can you tell me how big an electron is? Can anybody tell me how big an electron is?
I know this is certain power.
No, I mean, you know, electron's very elusive, so maybe it has zero size, you know, zero size.
There's no such thing as zero size.
There's no such thing as zero size?
Yeah.
There is. I mean, if you think of things as being this, you know, how big is a photon? How big is a photon of light?
Very small.
How big a photon's very small, tiny particle? No, a photon has no size, right? And so, I mean, if you get into all this nuclear theory stuff, right? And there's this Higgs field that they did at the collider, you know, the Large Hadron Collider. Yeah, which got shut down because some kind of electrical thing. But you know, this Higgs field, where how things pick up mass, you know, through the Higgs field. And so that's one way of understanding electron. Is electron can pick up mass through this Higgs field. But anyway, as far as gamma radiation goes, gamma radiation is a photon of light. A beta particle is an electron, and an alpha particle is the nucleus of helium atom. So alpha particles, yes, are much more massive than the other two. Well, maybe we should start. I was going to go out of order, but maybe I should go in order of this chapter. And so alpha particles, when the nucleus is unstable, you know, nucleus has got too many protons. One way of losing some of those protons is we can break off two of them as an alpha particle, and so the nucleus is actually changing. Well, what happens when you lose two protons out of the nucleus? Well, we'll see what happens. It's called alpha emission. But anyway, they have low penetrating power because they're going to react with whatever they come in contact. They're stopped by a sheet of paper. So it's easy to shield yourself from alpha particles. Here's an example of a alpha emission. Alpha emission is, you have something like uranium. This is uranium-238 with 92 protons. It's unstable, it's radioactive. We call radioactive nuclei unstable. And so therefore, you know, part of it breaks off, a chunk of it, and this chunk is an alpha particle here. And so we've just lost two protons. If we lose two protons, how many protons are left? If we lose, if we have 92 protons and we lose two of them, we're going to have 90 protons left. Right?
I thought you were talking about the
Well, we have 90 protons left. Well, it's no longer uranium. What element is number 90?
Thallium.
Not thallium. Thallium's Tl. Thallium's Tl. Th is thorium. Thorium. So we end up with thorium. And then we also, not only do we lose two protons, we also lose two neutrons. But do you guys remember the mass number? The mass number is the sum of the number of protons plus the number of neutrons. And so the mass number is going to change by 4 because it accounts for both the protons and the neutrons are lost. And so we lose 4 in terms of mass number, so we're at thorium-234. And so this is alpha particle emission. We can figure out what we're going to form based on adding up Z and adding up A. Right? And so predicting alpha emission is not difficult if you're given the radioactive, we call a radioactive atom a radioactive nuclid. You know, it's radioactive nucleus. Nuclid is for a single atom of a single isotope. It's a nuclid. And so uranium-238 nuclid, given that we could figure out. And so nuclear reactions, predicting nuclear reactions is not that hard if you know what an alpha particle is. You know what an alpha particle is, then you can predict what the product is from alpha emission just by adding up the numbers or subtracting the numbers. Beta particles,
How do you know how many particles are going to be emitted?
you just do one. If you do alpha emission, you just do one alpha emission. We could see example. Do you want to see example of that now or later?
Yeah.
Oh, we'll do an example later.
How do you know it's not going to keep going from,
It will keep going. You're going to get a series. And we call it a radioactive decay series or decay series. And a decay series is going to occur by different types of emission. You'll have alpha emission, beta emission, gamma emission. Gamma is not going to change the nucleus, but the betas will because,
Wow, I mean, if it could be stopped by a sheet of paper, like why do they say radiation is so harmful?
because of that point, that's only one step.
Yeah.
If you look at uranium, there are a bunch of steps, like tens of steps in the decay process. And a lot of those steps also emit gamma radiation. And it's that gamma radiation. Alpha radiation is also bad, but it's the gamma. I mean, you don't want a whole bunch of alpha.
Gamma, you said it's a photon of light.
Yeah, a high energy photon. You know, gamma radiation is much more penetrating, much more damaging than X-rays. You know, so you need lead bricks to protect yourself. Beta particles, you don't need lead bricks to protect yourself. For beta particles, all you need is a sheet of foil because electrons, can join the sea of electrons in a piece of metal, right? And so, but these electrons are very unusual because these electrons don't originate from the core electrons. They don't originate from the valence electrons. These electrons actually originate from the nucleus. And so how can you get an electron from a nucleus? Because are there any electrons in the nucleus? There are no electrons in the nucleus at all. But what happens is this. You know, what's important also is the neutrons in the nucleus. We shouldn't ignore the neutrons. The neutrons are thought to be the glue kind of that holds the protons together. If you didn't have any neutrons, then you can't have very large. But you don't want too much glue, apparently, because if there's too much glue, then the nucleus becomes unstable. And so what can happen in the nucleus is a neutron can get converted into a proton. When a neutron gets converted into a proton, it emits beta, which is an electron, and high energy light, like a gamma. And so here, the beta is accompanied by gamma, or X-ray emission, depends on the energy of this. Take a look at that. But what is a beta? A beta is given this symbol or an E, so it's either beta or E. Beta has a mass number of 0 because there's no protons, no neutrons. But its Z is a -1. And so this is what happens here. When you add up a beta plus a proton, 1 minus 1 gives us back 0. A neutron is going to have a Z of 0. It's neutral. Z is the number of protons, positive charge. And a mass number of 1. And so we add these up. 1 minus 1, 0. 1 plus 0 is 1. And so they add up like this. This photon you don't have to worry about necessarily. So typically when we have beta emission, this is what we're going to have. You just got to memorize the particles. So, alpha particles written like this, He24. A beta is written like this, -1, 0, or E -1, 0. So we'll just use that.
In terms of masses, does the proton plus the beta plus the energy of the proton add up to?
No, they don't. The masses don't add up. The mass numbers, of course, will add up, but the mass numbers are not mass. The masses are going to be different. Yeah, the masses are going to be different because we have this. Actually, nuclear chem is easy for predicting energy changes. Delta E, which we'll call E the energy, is equal to mc squared. But the only thing that changes is the mass, because m, c is a constant, so it's actually delta m. And so if there's any kind of energy change accompanying a nuclear decay like this, and there is, then the masses aren't going to add up. But we can figure out, And so the mass, remember the mass defect in chapter 2? It's the same kind of thing. We're going to get a mass defect in these. So we figure out what the mass is from here. How do we determine the mass? What is the mass of thorium-234? It's close to 234, but it's not 234. It's close because neutrons and protons make it up, and they weigh about 1 AMU. But we got to figure out the isotopic mass. Do you remember isotopic masses? How are isotopic masses typically determined? No, isotopic masses are not the average. The atomic masses are the average of the isotopic masses. The isotopic masses themselves are determined with a, not a mass balance, but a mass spectrometer, right, mass spectrometer. And so what we get is we get the mass of this to as many digits as we can, we get the mass of this to as many digits as we can, and we have the mass of this. And when we add up the masses and then see, do they match? And the masses aren't going to match. The difference is going to be accounted for in terms of the energy here. It's released. Okay, the in nuclei, the proton to neutron ratio is very important. And so if we have too many neutrons, that's no good.